Cisco Internetwork Design. Now, the Internetwork development process can be divided into three big picture phases. The first part, design, then implementation, and then ending up with management. Well, we've talked a lot about implementation and management in this series, so we're going to dedicate this nugget to design. Now, a lot of people say that design is the most important part, and I agree with them because the saying, measure twice, cut once, really does apply. All right, in this nugget, we're going to start out by looking at a few common goals that are found in any internetwork design. From there, we're going to move and talk about a number of devices that we can use within our network, and we're going to end up talking about a popular network design model. Now, keep in mind that as we look at these goals, we're only going to look at 6 of them. And what we're talking about here is just common goals within any internetwork design. But what does that mean? That means in the network that you actually build in the real world, you're going to have more goals than this. And in fact, in some special cases, maybe 1 or 2 of these won't be included, but for the most part, they should always be included because they're identified as common goals. All right, let's start up here. First thing we're going to talk about is functionality. Now, when we talk about functionality, we're talking about what are we building this network to do, the action, right, the verb. What do we want to accomplish here? So, within functionality, we're going to find the option of different protocols. When we talk about protocols, we're saying within this environment, what kind of languages do I want to be able to speak? Some examples, IP, DECnet is another example, IPX, and then on down the line. As you can imagine, there are a number of them there. The most common is going to be IP. That way we can interface very well with the internet network known as the internet. Okay. Now, the other thing we need to talk about is not just the protocols as far as passing information between all these devices, but also routing protocols. In a small environment like we see here, 2 routers talking to each other, you may not need an automated routing protocol to figure out which path to take. But in a large internet network where you have a number of routers, you probably will. Some of the choices you can see here, RIP. Another one is going to be IGRP. And in larger enterprises are going to use OSPF. There are others that you could use as well. Now, beyond protocols and routing protocols, the most important part of the functionality that we're going to define here is going to be found in the applications that we allow to exist within our network. Let me give you some examples. We're going to draw the application down here. In fact, let me get you familiar with our drawing. Right here, these boxes with the 4 arrows in them are lower level switches. The more arrows in these boxes show a higher level of switch, more port density, bandwidth, things of that sort. Circles with the X's, as you're probably used to already, are routers, and we talked about that here with the routing protocols. Well, when we're going to have applications, we're going to assign those somewhere within this network. Let me draw it out right here. One of the applications we could have could be SMTP. This is a simple mail transport protocol, and it's going to provide, obviously, our mail functionality. Another one might be SNMP. This is where we're going to find some reporting. And then some other example would be FTP. As you might note here, all of these are popular IP applications, right? TCP IP. And because that's the most common form of internetworking that you're going to find, that's the examples that I use. But they could be other things, right? All right. The next thing we're going to talk about is cost. We're not talking about trying our best to keep the cost down, and we're not talking about spending more than we need to or just getting the Cadillac service within our network. Really what we're talking about here is just getting our money's worth, making sure that we're spending the money that we need to and getting the exact functionality that we need out of it. Now, this is the big thing. There have been a number of projects I've been involved in, and in all those projects, anytime a project has gone over as far as budget, as far as dollars, it's because of this. It's because there wasn't a good idea as far as the total cost of ownership. Now, what do I mean by that? I mean, we can estimate how much these devices are going to cost. That's not hard, right? Because we can go to the vendor and say, okay, what kind of deal are you going to give us? What kind of points are you going to give us? Once that's decided on, we need to figure out how many man hours it's going to take to get these devices up and running, more than up and running. If we have to have any form of redesign or any emergencies, we need to budget for that as well. That's very hard to do, and that's why we run into this total cost of ownership almost always running over on projects. So be aware of that and try to calculate that as best you can. All right, the next thing we're going to talk about is manageability within our network. Now, as you might be able to tell, if you break this word out, really all we're talking about is the administrator's ability to manage the network, right? Well, there's a number of ways to do this. This can be done manually, and that's a matter of taking trips to each one of these devices, and making sure that they're performing as they should, looking at counters, things of that sort. Another way that we might be able to do this, and my recommendation, is find an automated method. One example of an automated method, as I wrote down here, is SNMP. That's a simple network management protocol. All right, in its default form, SNMP is going to be able to provide you with generic information. What I mean by that is it's going to be specific to the device, but the type of information that you can collect is going to be generic. You're going to get like input packets, you're going to get output packets, things of that sort. Now, the way you're going to collect that is this. Let's say that I have an SNMP server, as I defined down here. It's going to be connected into the network in some fashion. It has the ability via this protocol to go out and monitor other devices, let's say this SMTP server, and gather some information off what's called a management information base. This is where I get that idea of the information being generic. This is a CAN management information base. Now, if you want, you can get specific. A vendor can offer what's known as a vendor-specific MIB. In other words, they're going to let you collect information that might be available on their devices but not others, right? Well, there's a form of that within Cisco, and most of the time, if you want to get Cisco-specific information off of devices, you would use Cisco Works. Hopefully you're already familiar with this. It's a very powerful tool. In fact, it's a lot of tools put together, and you can use them individually if you want. But basically, it's just there for the manageability of your network. Now, another example of what you can use would be Armon, the remote monitoring, to get some other base-level statistics. All right, the next thing we're going to move into is reliability. Now, when we talk about reliability, we're talking about redundancy. Now, there's a simple redundancy that we're going to find within hardware, and here's an example of this here. Let's say we have one package here that's identical to this package, and then these switches have access in this, and so that if one failed over, going down this route, this switch can go over here and then still get to this top level design, but just another path, okay? So that's hardware redundancy. This is the trick, though. There's two ways to do that. First of all, if we have that failure, do we rely on the administrator to come manually configure that? In other words, there's some alarm that goes off, says, hey, you know, this is down. Do we run over and switch over that configuration? Or is it a matter of doing that automatically? Obviously, you know what I vote for, right? There's a number of protocols that we can use for that. One example is the hot standby routing protocol. Another is VRRP, where we're going to find redundancy. Either way we go, there's going to be a series of messages between these devices to recognize whether they're up or down. As soon as one of them fails, being the primary, the secondary is going to take over. Really cool stuff. Now, the last two goals that we're going to find on this next whiteboard are going to be scalability and adaptability. They might almost sound like they're going to be the same, but there are some differences there. Let's cover what we're talking about. With scalability, we're really talking about establishing some headroom. Now, a lot of times when you talk about establishing that headroom, most people are going to go ahead and think that we need to go ahead and go plus size on bandwidth and plus size on port density. In other words, places to plug in devices, right? Well, that is true. I mean, that's going to be part of it. We want more bandwidth and we want more physical plugins, but at the same time, you know, you can take that outside of the idea of, well, here, let's go. The first example for this hardware type scalability, we're saying, all right, we need 48 ports for our current user base. Now, there are some options here. Either we can go with two 24-port devices, or we can go with one 48-port device. Or what we can do is we can build one device that is going to be a chassis, right, like this, that's going to allow you to have a number of cards in there. Let me draw another card there. And what you can do is you can say, okay, I'm going to fill these two slots today. I'm going to have two slots open for future expansion. In other words, that's scalability, right? All right, this is the hardware example, but let me give you another one. Let's say that we have a network, and in my years of building networks, I've seen that a lot of companies start small. They build a small local area network, and in doing so, they address their devices, right? Each of these nodes out here. In some cases, they'll just pick addresses out of the sky. Now, because they're not connected to the internet, it doesn't matter when they have this separation between the internet and that network itself, right? They can use anything that they want. It's simply logical addresses at the IP address space. But what happens when this network continues to grow? It gets larger and eventually connects to the internet. What we had to do is have a rework of all the IP addresses. One of the biggest headaches you have ever seen. Well, you know, if we were looking at scalability, while this network was young, what we would do is we would use the private addressing that you're going to find in RFC 1918, and you would use NAT on some device. Might cost you a little bit more on that device so that you have NAT support, but this is what we would do. We would have private addressing here. So in other words, let's give an example, 192.168.1.0 as far as our network number there. And when it's a private not connected over here to the internet, no problem. Everything runs as it should. And then at the point that we finally get this connectivity, we put a NAT device here that's going to translate that private address into a pool of public addresses, then we have no problem either. There's nothing to change over. That's what we're talking about when we hit scalability. All right, let's move on to adaptability. What we're talking about here is an ease of migration so that we can support future technologies. The only thing we're really talking about here is we want to avoid a forklift upgrade. So you've got to talk to your vendors and say, okay, if I buy your device today, looking down the road, I hear the buzz about whatever it may be. Let's say a couple years ago, it would have been, I hear the buzz about voice over IP. This chassis that I'm going to buy now, will it or will it not have support for voice over IP? What do I need to do to follow that trend? If it equals a forklift upgrade, don't do it. If you can do it without this, then you say, okay, that's worth the money. And that does it for our common goals. Now what we're going to move into is the devices that are available for our inter-network design. All right, these are going to be the devices listed here, and what we're going to do is we're going to go through each and give an idea as to what they may be used for. As we go through it, you're going to kind of see the evolution that went through networking and how a hub, having been a popular answer in the past, really isn't much of an answer in today's environment. Same thing with the bridge. Let me start with the hub here. All right, what we're talking about when we talk about a hub is simply a multi-port repeater. Remember that when we first started networking, what there was out there was a problem, in fact, let me draw it out, with a device, let's say N1 here, transmitting a signal, all right, ones and zeros, and then that signal kind of degrading, not going as high, the corners not being as clean, whatever it may be. So what you had to do was hit a repeater after a certain amount of distance, and it would recreate that pattern as clean as when it started, and then eventually it would get over to N2. So it's simply a way of bridging the distance between two devices. We had one port in and one port out. Well, then somebody said, why one port each time? Let's go ahead and make a multi-port repeater. Going to look something like this, and have that functionality for a number of devices. And now we have a center point for our network. This is where we actually got the hub and spoke design. Makes sense, right? The hub, as it's named, is here in the center, and it goes out to the different devices, N1, N2, N3, and so on down the line. In fact, this was such a big breakthrough because before we had that shared bus, if you will. We had, let's say, let me give you the example of 10 base 2. Let's use that. We had a coax cable with a terminator on each end, and then hanging off of here, we'd simply have those BNC connectors going to our devices, N1, N2 here. But the problem was, as soon as we had a problem on this backbone, this bus here, it affected both of these devices. Well, check it out. On this hub and spoke, if you have a problem between the hub and N1 right here, it doesn't affect any of the other devices. That was the big thing about the hub and why it came into existence. Next thing we want to talk about is a bridge. When we talk about bridges, we're really talking about layer 2 devices. Keep in mind here, on this hub, we're just talking about layer 1 devices. In other words, when information comes into this port, it's going to be the ones and zeros, right, that we would see there. Those ones and zeros simply get recreated or cleaned up and sent out to another device. Well, that's not true here. With a bridge, we're talking about layer 2 functionality or awareness. Now the addressing at that layer, as you know, is the MAC layer address. So here we go. Let's say that I have N2 here and it wants to communicate with N1. We'll just draw this a little backwards this time for the sake of flavor. And then we're going to have our bridge here. Now bridges were commonly 2-port design. In other words, I'd have one connectivity into one device and another into another, or networks, and what you're going to find there is simply the ability to say, okay, I have a MAC address here. For the sake of our argument, we're going to shorten it just to 01, and the MAC address here, 02. I am able to know that I need to go from 01 to 02 in this environment here. And because I have this MAC layer awareness, there can be some filtering done there if you had to, right? Well, it's going to be slower than that multi-port repeater, but it gives us a bit more control. All right, these are the popular answers back in the day. Then came along switches. Or you can say then switches came along if you want to sound like you have a higher than a 6th grade education. Sorry about that. All right, when we talked about switches, we're still talking about a layer 2 device, but what we're going to buy ourselves here is more port density in the design. So to give you an example here, we could have a 1U thick switch with a number of ports. Now, why were we able to go higher within the port density? And the secret is this, than we were with the bridge, is the matrix backplane that we have on the back of this device. The matrix backplane allows for high-speed exchange between these different ports. Here's the beauty of the thing. Because we're talking layer 2, when I have N1 here and N2 here, the communication path is going to be like this, going into this device, going through here to another port, and out to N2. That's cool, but the important part is this. When I have a hub up here, my collision domain is the entire hub. What do I mean by collision domain? I mean the ability, let's go back to this bus, for N1 to send something out on the wire at the same time that N2 does. If you do, they're going to collide. They're going to have a wreck here on this backplane, right? And that's going to mean that neither of these frames, or I'm sorry, neither of these packets or frames or data structures got to their destination, right? Well, the same idea can exist down here within a bridge, right? But simply it's chopped up right here. We're chopping collision domains up. Only can happen here. So if there's one device, it can't happen. More than one, then it can. Well, the switch said, let's take that into consideration and provide that as well. So my collision domains exist from a port to the device, from a port to the device, each individually. So it cuts down a lot of errors within the exchange of data. All right, so that matrix is going to make it faster. We've divided up the collision domains. We've increased our port density. What else are we going to buy with the switches? Well, the answer to that is security. And you know security doesn't come cheap, but in this case it actually did. It was kind of a side benefit from gaining multiple ports within this layer 2 device. This is what we get. If N1 sends a packet in, we have the ability, or it supports, one-to-one relationships. In other words, one interface coming in that is going to result in one interface going out. Because we have this layer 2 awareness, these MAC addresses, we can say that, okay, we see a source and destination on the frame, and that destination MAC address, when this switch looks into its table, says, hey, you know what, that's out port number 2. So it only goes out port number 2. Over here in a hub environment, anything that comes in goes out every other port except for the port it came in, because there's no sense of addressing. Remember, we're just talking ones and zeros, right? So this gives you a level of security. So an attacker can't just plug into this device right here and collect all the information that traverses that switch, because the conversation is going to be held to this point. Now remember, I said it supports that. Not always going to happen, because there's a learning phase of learning where MAC addresses are that's involved within a switch as well. All right, let's move on down to our layer 3 device, and that's going to be the router. Now we know that by definition, routers are responsible for providing what's known as end-to-end delivery within our network. So if we have N1 here, and in some cloud, could be a number of routers, hubs, switches, all of these things that we've listed above here, eventually getting over to N2, the responsibility for that delivery from point of origin to point of destination is going to be that of layer 3 devices, in particular the routers. How is it going to accomplish that? It's going to do that through routing protocols. We talked about that before, and that's communicated in between routers and paths that they're going to take. And it's also going to do that with what's known as logical addressing. This logical addressing, as far as IP, is going to be, chewing gum and walking again, having problems. All right, logical addressing. This is going to be the IP address space for our example. And this addressing can change as it needs to adapt to our surroundings, to what we have as work environment. We can add some, take something away, can move them back and forth. You remember that from legacy we've taught. All right, so these are our devices. Now, as I said, you're going to see the evolution. When we first started networking, the hub and the bridge were very, very common. Now, we really have just the switches, routers for the most part. There's a couple isolated instances where you have a hub, where you're not really about security, but in most cases, you have these two devices predominant within your network. Now, I want to show you some pictures so that you can get a familiarity of what Cisco offers within these ranges. Let's move on into that. Let's see here, right here in my document. All right, the first thing we're going to see here is a hub that's offered by Cisco. Remember, simply a multi-port. Saying, well, where are the moving out of the? We're going to do that and move. Are going to be able to perform as well. If a device performs as a bridge and a router, it's called a router. So you have that functionality there. So let's move. I'm going to show the 2950. I can tell if you don't hear the numbers I say. Cisco 29 series switch. This is going to be a switch. Those 24 arrows. This is what they're in functionality. This isn't one big switch. Look at the 2, 3, 6, 7. Now moving of switches, now we're going to see the 4000 series family. Probably more functionality within these blades. 1, 2, 3, and you can add different functionality. In cases, you're going to have a large enterprise network. We're going to need that switching capability that looks like this. House. And you see all the slots that you have. And because you have the higher, you're also going to have bandwidth, higher thing is going to increase exponentially. After that, we're going to get out of switches. At the again, an example of 2600. You see that it has a few interfaces to use to build your internetworking apart. Then you're also going to have the 3600 series, larger, as you can see. For the big, the availability is 70. 1, 2, 3 of them here, or the cards insert back to the battery. All right, that's enough for our picture tour. Now let's move back into what we're going to do. Devices. Now we need to move into the methodology, or what's known as the higher. In order to fully understand where it can be identified, simply extend beyond the layer 2. Remember that we had switch number 1, and all of those devices were in 2 and 3. Level here, even if connected nodes or servers, were relatively layer 1 and layer 2. We want more layers. We can look at these layers like we're talking, but also we're going to do what's known as modules. You're going to see those benefits down here. This idea of bringing ourselves from a hierarchical or a layer. We introduce routers into this, extend ourselves up to layer 3. That hierarchy in our network, and support our modules in our segment. Back to modules. What we're doing is we're taking a lot of concepts and breaking them down, and do that design, because you only have to, let's say aspect, let's say right, you only have to worry about access to the end users, or right, setting up server farms. You don't have to worry about high-speed transfer. Design is going to become easier when we break ourselves into this modular. It's going to affect. So let's say that I have network and I need to support more users. All portion of this model, let's say this duplicated right here, my model without a lot of rework, or I simply just clone this thing. Fault isolation here, because we understand that there are points between these different modules, doing that in their jobs and their responsibilities. A certain, you know what? All right, then the last thing, benefits is going to benefit what can be accomplished in phase here, and move myself support 10 meg transfers, right? Move to where I support 10, maybe even into the gigabit. I could do it here, and then here, then my network. These are the benefits. About talking about these modules within our hierarchical, there's going to be the access layer. responsibilities. So let's sign in those out. Access. What we're going to provide there is, remember I illustrated that one, so it can be, you want to give that connectivity. Now, at this, a lot of manipulation, a lot of filtering. You don't want to do a lot. You simply want to provide the, as soon as you move that manipulation, we want perfect. Now that out there, and also things of that sort. You also can do filtering at this. Bring in some type of manipulation of the data. Put in your security. Access layer is simply going to be made. Going to be low-end switches to provide connectivity. Low speed on offering 10/100 in most cases. So by low end, have a chassis, but all, as I'm saying, is these devices, in some cases to a gigabit. Then once I move this here as well, this is where I'm going to introduce my route, build access. Actually, a lot of people that must be going to layer 3. Not the don't coincide. Support the access here in the and layer 4, and here in the core one is layer switching, and a method to accomplish all our filtering here, and serve as a point for and the access. Can for information relying on concept of switching so that we can get information. Very high speed transfer. Known as wire chariot, we want it to move. What is that? Oh. Now it's important in your network environment, you may not have the core distribution. You got to this is that it's important model. In other words, you need to have that 3 existent within your points of segment time. It's going to be in each one of those layers. Let's start. Let's not just start at the bottom. Let me do them. All right, access down here, distribution. Access layer, as we said. Types of devices you might see. 2950. Remember I showed earlier. In fact, here in a second. You might also see a. It depends on port density. And at the high end of port 1000 switch. Again, simple connectivity and the bandwidth. You're going to have more ports. Pictures again of at least 2. Start out with the 2950 series, so you can see that you can interject any one of these switches. The 4000 series, like we said, higher port density. 6500 family ranges from a small. We're going to see possibly these right here. These devices, those types of connectivity from the distribution down here between these two devices, and the same thing can exist here. As you can see, drawing segmentation between, that's where we move to an enter here, router functionality. Gives us our layer 3 logical address, our filtering. This is where we're going to do a lot of and having those across the two, forming a level of redundancy. That type of connectivity, we could build that in as well. So at the distribution, back into our pictures and find the 2600 series router for the functionality, the 70 for those large. I just wanted to remind you of those pictures. We're going to be seeing, you can have 500s. And what's the difference? 500 down here. Other options would or the 5500 series on what you need in performance. These types of devices, this connectivity is going to exist here, but right and these transfers here are about gigabit support. Gigabit connections. Now that's approaching that wire speed. Data manipulation. We started out this nugget goals, and those goals were going to be just 6 network design, and they were function, manageability, reliability. The final one was adaptability. We talked about how these responsibilities there. We talked about the hub, switches, and routers. And then we ended the hierarchical model and how it in the more measurable modules, and it's easy that are associated with that. I hope